how would it work?
Yeah, I mean it's possible. I would say something like integrating Xscale Monitor into those types of tools. Xscale Monitor is just very easy to just run in the background. So I don't know if you necessarily want to integrate it directly into those things, but the others can definitely be combined together. Yeah.
I see. So, I mean, my question is not about integration, just like usability. It's possible that like
Oh
we
yeah,
can
yeah.
use it. Okay.
Yeah,
Perfect.
absolutely.
Okay.
Are there any other questions for Kyle? Okay, if not, let's give thanks to Kyle. Okay. So then we'll go to the final. We have 3 short talks by the students, and that's how we'll finish the thing. So we have the talk by Ben, followed by Gautam, followed by Nauras. Let me just introduce all 3 of them, and then we'll go quickly each presentation. So Ben, many of you would have talked already to him. He's a PhD student in the group. His research interests lie in the HPC, parallel computer architectures and network-based computing and programming environments. And specifically, his work is focused on offloading parallel programming models and computational workloads to SmartNICs. And that's what he will be talking today. And he actively contributes to the MIP software, and is also a student member of IEEE and ACM. So he will first give the first talk using Bluefield 3 SmartNICs to offload vector operations in Krylov subspace methods. The second one will be presented by Gautam. He presented one on Monday on the Cosmos system, but this is a new paper which will be presented at Cluster Conference, IEEE Cluster Conference, I think, 10 days from now. So he's a 4th-year PhD student in the department, in the group. His research focuses also on advancing the MIP library with a strong emphasis on GPU technologies while exploring also HPC and DL frameworks. And he's also passionate about optimizing energy and power efficiency in HPL DL workloads. The final paper will be presented by Nauras. He presented one of the IDL tutorials on Monday. So he's again in the group, continuing with his PhD. His research interests lie in the intersection of deep learning and HPC. He works on advanced parallelization techniques to accelerate the training of DNN and exploit the HPC resources. And he also is involved in this event. We didn't talk. We have a much more larger project which is going on Icicle, which is an NSF institute, which I lead, but that is a much more bigger. There are 13 universities. Several people here are also involved. So he's also involved in that project. So he will be talking on HyperSAC, distributed hyperparameter optimization for deep learning using resource-aware scheduling on heterogeneous GPU clusters. So we have 3 short talks. So why don't we get started with Ben, and then gradually we'll follow with the other 2. Or the password, I think. Matt? Huh? The password. Matt, where is that?
This thing on? Okay, cool, it's on. All right, so hi everyone, my name is Ben. I'll be presenting this paper that was led by my former lab mate Kaushik. He now works at NVIDIA. This is leveraging BlueField-3 SmartNICs to offload vector operations in Krylov subspace methods, kind of as a nice segue from Kyle's talk on MapIsh2 DPU. So for starters, just to go over the BlueField-3 DPU again, the latest one has 16 64-bit ARM cores, each running between 2.75 to about 3 gigahertz. Many of the models either come with 16 or up to 32 gigabytes of DRAM. The main motivation behind this work is that with the increased power of BlueField-3 SmartNICs, we can do more than just offload communication. Like Kyle mentioned, we can offload compute, such as anything from individual matrix, vector, VMA, distributed dot products, operations, to potentially full functions, depending on the complexity and amount of data required for that. So the pure thing of this is how can we offload these in the case of Krylov solvers. What are Krylov solvers? These are numerical methods. You could think of these as like level 1 BLAS operations. And the three main ones are distributed dot, matrix vector, and vector multiply add. So your common AXPY operations. So the second motivation about this is that in previous cases, we end up having what a user has to do, or what a developer has to do, is manually look at, say, a configuration graph like this, where you may have various matrix vector, vector multiply adds, distributed dot products, and even scalar ops, and see how to manually offload these to a BlueField-2 or BlueField-3 SmartNIC. And these can take a substantial amount of program time, just depending on how much you send to the DPU. So there's kind of two components. There's kind of two components to the question of how do we do this appropriately. One is, what do we intelligently offload? The second part is, how much do we offload, and can we determine that also intelligently? So we propose a few things here. Firstly, we propose a general splitting scheme, and I'll get into what that means in a minute, to offload, say, PCG algorithms, or to split operations onto the host and DPU. We look at this notion of an onloading scheme, which I'll also get into later, and then we look at two benchmarks that utilize these Krylov operations on two different test beds. The motivation behind these two test beds is that on the first test bed, with Broadwell CPUs, we end up using these are fairly slower, older cores. So naturally, you're going to get a massive benefit when using BlueField-3 SmartNICs. Our second test bed, even though it's only one node, it is a later edition of the Sapphire Rapids. This one doesn't have the high bandwidth memory, for example, but it's still a later processor. And so we may not see as many benefits depending on the problem that we're dealing with. So for starters, let's get into the splitting scheme. Every application that uses that runs either within or over PETC has these Krylov operations. The high level is that we take our splitting scheme to put a portion of these operations onto the host. We put a portion of them onto the DPU, such that neither operation involves such that there are no real data dependencies immediately required by both of these, so that when it comes time to when you get to a synchronization point, all the data can come back together without any loss or invalidation, so to speak. For this, we have a very straightforward algorithm on the bottom right. It's just going through and saying if we have a path, basically if we have a path for any operation, we can we can add the dominant path to our host operations, add non-dominant items to our DPU, and perform a topological sort to output a graph. So for a user or for an advanced library like MapIsh2 DPU or some others to effectively utilize this and offload operations to the DPU. Getting into the onloading scheme, we have we take motivation from a default offloading scheme before going to something a bit more advanced. By that I mean, when we're using an offloading scheme, every CPU process is going to offload to a proxy process onto the DPU, and these proxies are going to get everything. but that becomes expensive when we have an increasingly large problem size. And if we're dealing with computation, that just makes things much less efficient. In this case, we adopt a multi-leader approach similar to, say, hierarchical collectives or hierarchical operations, and we have leaders offload their work to these proxy processes, and then any non-leader based process on the host ends up just sending their work to the leaders. So there's still this overlap of compute and communication, but now there's some overlapping compute with each other, so to speak. Again, we have our two test beds. In the case of test bed 1, these are older. Again, these are older cores, but they still end up using the same network and same SmartNIC. And then our second test bed ends up only having one CPU, but it's again, Sapphire Rapids. You're going to get a much more computationally powerful processor. So here, I'll start with the onload scheme. When we do multi-operation offload, we end up getting this up to 38% improvement for a given problem size at full subscription. So we're saying one node, full subscription, 96 processes on that one node, and each DPU process is going to get 6 of these, or is effectively getting assigned to 6 of these workers, or 6 of these host processes. While in the largest problem size, we end up seeing up to 38% improvement, we still see a proportional amount, more or less, even as we decrease the problem size. So there's an equal distribution of work from the host to the DPU, even in these smaller cases where you may not necessarily need the DPU, but it actually ends up helping out that much more. Because if you think about this, going just from 10 seconds to 8 seconds to, like, say 8 or 6 seconds is one thing. Think of how this would occur if you had a simulation running for days or weeks. That 38% improvement cuts down significantly. And similarly here, depending on, and similarly here on the second test bed, if we're going to offload a certain portion, or if we're going to offload a portion of the work from the host to the DPU, different amounts depending on the test case will end up ultimately resulting in better performance as well, because we're based both on the compute, which stays the same for the most part, but more importantly on the data transfer. And here's some more results where we're through strong scaling and a bit of weak scaling, we can see up to 10% or 24% benefits depending on the test bed. For the pipe CG benchmark, this is a 27-point stencil, so this is already complex within its communication, but also compute. And similarly, if we're going to do the same thing with this AMD PCG benchmark, we get up to 22% benefits on our second test bed, again, thanks to the older host nodes, but still 10% on the more computationally powerful Sapphire Rapids. That pretty much wraps us up. The future work that Kaushik and I were going to time pending was look at other algorithms, fast Fourier transforms such as Hefty, for example, or P3FFT, and other algorithms for linear algebra operations such as finding eigenvalues, and many others. Hardware pending and availability, we're hoping to look at, say NVIDIA HGX machines where you have, say, 8 GPUs, 8 SmartNICs with those. And so just thinking, okay, what happens if we have multiple SmartNICs? Can we extend this to, can we send this to a multi-DPU system or multi-DPU node, for example? Just that's something to think about. That's really it. Thank you for your time. Any questions?
Questions for Ben? Okay, let's give thanks to him. Oh, there is a question from Pankaj.
Yeah, Pankaj?
Yeah, hi, TK. Just very quickly. So is this a profile-guided optimization for splitting or some other method?
Not so much profile. It's not profile guided. It's more so like control flow graph or data flow graph guided. So given the, for example, I can get to it. Given the particular flow of operations, where the motivation for the algorithms and the design is which way does the data go? Does the data from the preconditioner is it or where does it go to operations such that if an operation is not if an operation is not immediately relying on it, we can potentially offload that operation to the DPU. Or if it's not reliant on it at all, then we can offload it to the DPU.
And
Otherwise,
the
it's stated
compiler
on
is
the
doing this, or?
not the compiler. It's the way that the framework works is that we do a pass. There's a pass through the application that looks at the major operations, and these operations are predefined in the framework just to keep things simplified. So it's a little static, at least in this case. But future iterations will try to make it more dynamic. So that way, we can expand to other operations besides, say, level 1 BLAS. Does that make sense?
Yeah. Thanks.
No problem.
Any other questions? Okay, so let's then move to Gautam. Thanks, Ben.
Hi everyone. So in this talk, I'll be talking about our recently accepted cluster paper at 2025. So this is on towards a dynamic message passing protocols for stencil-based communication patterns. So I'll be talking about introduction, and then we have 2 motivations for this paper, and then we'll talk about the designs, the results, and I'll then conclude. So to introduce, so we know that like Halo Exchange communication patterns occur in many stencil-based HPC applications like Mini-AMR, Mini-Ghost, and Milk. So in this pattern, typically each process often performs both internode communication as well as intranode transfers. So, and depending on the input parameters, like processor grid size, as well as number of parameters, so the internode and intranode communication time can vary, and the dominating factor can be changing. So effectively managing these diverse communication patterns is actually a challenging, especially given that given the dynamic nature of all real-world applications. So our goal is to propose a dynamic message passing protocols that can significantly optimize this communication time for these kind of patterns. So for the motivation part 1, so we know that like by changing the application parameters like problem grid size and number of variables, etc., significantly affect the message size. As you can see that on the left side, we kept the grid size as constant for Mini-AMR, that's 32 cross 32 cross 32, but then we varied the number of variables, and we can see that the message size significantly varied. And on the left side, we can see that we made the number of variables as fixed, like 10, and then we varied the problem size, and then again, we can see that the message size is significantly varied. So to address this, the existing work stealing solutions for intranode communication was proposed, but then they are like static and on-demand they follow static and on-demand chunking scheme. It means that it has a fixed number of chunks, and it is also not very practical to tune for every particular message size and every different CPU architecture out there. And the second point is, even then, like there are some fixed protocols they're using fixed protocols for a given message size, and we believe that like a work stealing has an additional overhead. So for certain message sizes or for certain scenarios, often switching to a basic protocol might be doing much better than using a work stealing designs. So this is the motivation too. We saw that there is some problem with this rendezvous protocol. I mean, it doesn't guarantee you any perfect overlap between the intranode and internode transfers if you have any in your application. On the right side, you can see that you can see that there are 2 nodes and 2 processes on node 0 and 1 process on node 1. Say if you get an RTS, intranode RTS before the internode RTS, then you cannot perfectly overlap because the rank 1 will be busy doing the intranode transfer. But then an ideal overlap situation can be you getting an internode RTS before the intranode RTS so that rank 1 can schedule the RDMA read and HCA can take the will start performing the copy operation. And then after receiving the intranode RTS, the rank 1 can perform the intranode read. But then this all depends on the order in which the control messages arrive. But then we all know that in a real world application, we cannot predict the order of all these control messages. For example, we also profiled this 7-point stencil communication benchmark with 4 nodes, 144 ppm, and we compared OpenMPI with our MWPitch Plus. So the blue bar indicates total normalized latency, and the orange one denotes intra-node only communication, and the gray one denotes inter-only communication. So if there is if we can do a perfect overlap between intranode communication and internode communication, ideally the latency should be the green bar, right, which is internode latency. But then we can see that there is a difference between the gray line and the blue line. That means that there is a potential for an overlap here. And we see that it's around 1.3 times overhead. So I will quickly talk about some designs over here. For intranode communication optimized, we use a dynamic work stealing concept. For that, we introduced 2 queues. First one is SPSE queue, which is single producer, single consumer queue. And the second queue is a single producer and multi-consumer queues. So we use SPSE queue mainly for exchanging the control message sizes and metadata. And we use SPMC queues for doing our work stealing designs. And we also use a bitmask to track the number of work stealers available, and I will be talking about that in the next slide. So this is our a dynamic stealing protocol design. This is a receiver-initiated design. So from the center side, the sender will only enqueue the RTS message, and then it waits for CTS if it is a cooperative design. So if the receiver thinks it's a cooperative design, or it waits for the finished message if a receiver thinks it's a get-based protocol or a work-stealing-based protocol. So from the receiver side is all the thing that happens. So the receiver will, to start with, it uses a predefined chunk size, let's say 1024, and then from the subsequent iterations, using the bitmask that I told earlier, it tried to figure out number of work stealers available in the previous iteration, and then based on that count, it either figure out whether to use a get-based protocol if there is only one stealer that is available, and if there are 2 stealers that is available, then we can do a cooperative-based protocol, and if there are multiple stealers available, then it will use a work stealing protocol. This is the main chunk of the design. And for the internode optimization design, what we did was the key idea is for all the stencil-based applications, we saw that they will be using an auxiliary buffer, and it doesn't directly use the communication buffer that it is passing to MPI library. So we use that as an opportunity, and then we proposed a simple extensions to MPI. So basically, I will be talking about. So these are the 2 simple MPI extensions that we introduced, we proposed. So one is what essentially what we are trying to do is, so we are asking the application not to pass any buffers. Instead, it just pass a null value as a buffer, and rather it expects a buffer from directly the MPI runtime. And using the MPI X get receive buffer, MPI runtime can give the application the receive buffer, and it can use that. And once it is done with that buffer, it can just release the buffer using the release buff API. So yeah, going to the results. So this is the results with mini AMR. We can see that we got approximately 37% improvement for a fixed process count up to 128 and varying the grid sizes on the right side. And on the left side, you can see that we got almost a 19% improvement for a grid size of 32 cross 32 cross 32 by varying the process counts. Similarly, we also did a 3D stencil. We evaluated 3D stencil benchmark on 4 nodes, 144 ppm. And we almost got 67 to 94% at scale at 2 MB transfers. And we got 32% better performance at 256 kilobytes. And then we can also see that for 2 MB message size, the proposed scheme performs overall of latency of 38% better on 4 nodes and 50% better on 16 nodes. Yeah, to conclude, so basically we identified this shortcomings and we in existing MPI rendezvous protocol, and we proposed APIs using which we can optimize intranode as well as internode communication, and we can overlap intra and internode communication on these kind of patterns. Yeah, I think that's all. Any questions?
Questions? High throughput presentations. We have to.
Are you changing the applications?
Sorry?
Are you modifying the application code with this?
So yeah, you don't have to modify a lot. So you can use the same normal MPI I send and MPI I receive. But then for MPI receive, I receive, you just pass null as an input parameter instead of the actual buffer. That's the only change that we need. Yeah.
Okay, so let's give thanks to Gautam. Then we'll go to the final presentation to be done by Nauras. Let's share the slides.
Okay. Thank you for staying until the very end. My presentation will be short, I promise. So this is HyperSAC, distributed hyperparameter optimization for deep learning. So most of the tutorials and presentations that we gave in the past couple of days talked about distributed training, right? The different parallelism schemes that we can perform, the data parallelism, the FSDP, tensor parallelism, and all of that. But all of these assume one thing, which is we already know that training configuration we want to train the model with, right? So we know the model architecture, we know the learning rate, the batch size, and so on. But these different hyperparameters need to be set prior to the training by the user. And usually this is done manually. So the user will sit down, try different configurations, and then, okay, decide which one is the best one. And this is based on trial and error and also experience. But there are also automated strategies to do HPO. These, however, are very compute intensive because you can imagine that the single training takes a long time, requires a lot of resources, but now we want to run a lot of these training experiments to decide the best configuration. So it is very, very compute intensive. The current strategies also underutilize the current existing hardware. So we ran an experiment with different lightweight to mid-size models on A100 and H100. So we tried both vision models, CNNs, vision transformers, and also language models. Like the Pythia model, which is GPT-like architecture. And we noticed that with these models, the GPU utilization is very low. So it goes from around 22% up to a max of 50%. So there is underutilization. And that's due to two factors. One, there's not enough workload to be processed in parallel. And two, there is data loading bottleneck, right? So if you have many experiments that are running at the same time, and all of these need to load data very, very quickly, because also the computation is quick for these lightweight models, then data loading becomes a bottleneck. So how do we address both of these issues? So we tried to formulate this problem in a more formal way. We call it the GPU assignment problem, or GAP. So you can assume that you have a job queue. These are all the different experiments that we need to run in order to optimize the hyperparameters. And as you can see, each job has a different weight, which is the occupancy that is required on the GPU. So basically, how many CUDA cores does this job require to operate on the GPU? So we have like so many different options to place these jobs on the GPUs. So depending on how many GPUs we have, how many nodes per GPU, and also obviously the weight of the experiment itself. So like, how do we decide the optimal placement? And we tried to formalize this problem as a multi-knapsack problem. But these are the main challenges that we try to address. How can we schedule the training jobs in an optimal way? What are the hardware constraints? So other than the GPU occupancy, right, like the computational aspect of the GPU, what are the other constraints? Maybe there are like CPU constraints that we need to consider, or memory constraints. How can we design a framework that just takes the workload and figures all of this out underneath? And how can we analyze the job requirements? So in the previous slide, we're assuming that we know how much like GPU compute is required for a certain job. We also assume that we know how much memory is needed. So how can we analyze that? And how can we keep track of the like GPU state itself during the experiments? So one thing that we take advantage of to run these experiments more efficiently is MPS, NVIDIA Multiprocess Service. And it's a feature that enables different jobs to run on the GPU. Each job will have a dedicated and secure GPU address. So if you don't use MPS, if you just run multiple jobs on the GPU, it's gonna context switch between these jobs, which is not very efficient. MPS will logically divide the GPU for these different jobs. So it's a server client paradigm. You have a server, and then the clients will submit their workload, and you can dynamically allocate the resources for each job. So this is HyperStack, the framework that we propose. So on the very low level, we have the HPC system, the hardware itself, file system, and multiple nodes, each with multiple GPUs. Then we have the hardware toolkits and libraries. So we use NVML to basically monitor the GPUs, MPS, as I mentioned, CUDA and cuDNN. And then we support both PyTorch and TensorFlow. And then HyperStack itself sits below the HPO job or the search space. So it has multiple components. One of them is the sampler. The sampler will run a very brief experiment at the beginning of the HPO workload to capture the requirements that are needed. So only a few iterations in each case, and that will help us in taking better scheduling decisions. Also, the sampler will keep a history of all the previous jobs, so you don't have to rerun experiments. Then the grid will define the search space. So the search space can be multidimensional, can have 5, 6, 7 dimensions, depending on how many hyperparameters we need to tune for. The state will keep track of the both the job status and the GPU utilization and state. Also support both resource elasticity. So if we have more GPUs available, how do we deal with that? Or if some GPUs are down, how do we take care of that? The policy is responsible for making the scheduling decisions. So we propose 4 different policies: first fit decreasing, worst fit, and worst fit decreasing. First fit will just fit the job on the first GPU that satisfies the requirements. Decreasing means we sort the jobs in a decreasing order. And then worst fit will give priority to the GPU with the most compute capacity available. And decreasing is just the same thing. We're going to sort it in a decreasing order and fit these jobs. All of these are greedy algorithms. So that means the scheduling decision is very quick because it happens in a loop, right? So if you look at this workflow, just look at 5, 6, 7, and 8. This is a cycle, right? So every time a job is completed or every time a new GPU is available on the system, we take a new scheduling decision. So this is the experimental setup. We experiment on 2 systems, Ascend and Lone Star 6. Ascend has the A100s, and then Lone Star has both A100 and H100. We perform some hybrid experiments on both of these GPU architectures. Models, as I mentioned, we have language models, vision models, both transformer and CNNs, different data sets. And then the baseline is the standard HPO scheduling scheme, which is just the one job per GPU. And these are some numbers with the different scheduling policies on different workloads. So we see there is consistent speed up of about 2.5x to 3x, but we also see that the worst fit decreasing greedy algorithm is the best one for two reasons. One, it achieves the maximum overlap between the long and short running jobs. So that's why we sort things in a decreasing order. We basically want to schedule the long jobs at the very beginning and then overlap them with the shorter jobs. And then it achieves the workload balancing because it always selects the GPU with the maximum capacity available. So we make sure that all the GPUs have some work to do at any given time. And this is just comparing the occupancy achieved on the GPU on average if we use these different algorithms. The baseline will give us the optimal placement so that we have like a point to compare to. So as you can see, we achieved 98% with the worst fit decreasing and 100% on two different search spaces compared to 99% and 100% with the optimal placement. But as you can see, the optimal placement takes around 3 minutes to finish, whereas this is in the millisecond range. And then this is some scaling numbers. This is only on A100. We see around 2.5x improvement, going from 4 to 8 to 16 GPUs. And the other figure is with both H100 and A100 combined. So since these different GPUs have different compute capacities, so the scheduler needs to be aware of this difference. And we see a consistent 4x improvement in that case. So the conclusion is the existing HPO strategies do not really utilize the newer GPU hardware architectures. Assigning multiple jobs per GPU can help improve that. If we do that naively, however, it's not going to give us good performance. In fact, it might hurt the performance. And we refer this as the GPU assignment problem. We map it to the multi-knapsack problem. And for future work, we plan to extend this with more scheduling policies. So as I mentioned, the policy component is replaceable, right? It's a modular design. So you can just, if you have your own policy, you can bring it in and use it. And we also want to try this on different GPU architectures like AMD and Intel. The full paper is available on the IEEE Explorer library. So please feel free to check it out. And yeah, I'd be happy to take any questions. Thank you.
Any questions for Norris? Yes, Sanjay.
Thank you for the presentation. One of my question is, so this looks like a pretty small scale model training because I'm wondering about the hyperparameter on LLMs.
Yes.
If we goes to extreme scale,
Yes.
I don't know much about it, but LLM does have such hyperparameter like such small models.
Yeah, that's a great question. Yes, large language models do have their own hyperparameters. However, like the state-of-the-art methods will take this very large model, right? Maybe billions of parameters. We'll scale it down. So take the shallower, smaller counterpart and do the hyperparameter optimization for that smaller model. It's called mu transfer. So basically you transfer the hyperparameters from the small model to the bigger model, but still you need to train the smaller model, right? And like a method like this will help you schedule the smaller model training.
Thank you. Just one more question. So I also investigate this kind of scheduling issue problem before. One of the major thing is how can you, if there's a new job for the scheduler, how can you know about the memory peak or compute usage for the new workload? So can you adapt such a new workload, or can you handle it?
So the thing with this specific workload, the HPO workload, is that you know every experiment you want to run in advance. So you can run all of them in the beginning for like a short time just to profile things and then estimate what is the overall execution time and how much memory is needed and so on. But this can also happen dynamically, right? So as you receive the new job, you can run it for a short time, see how much it requires, and then basically make the scheduling decision based on that. Of course, there are some analytical models that you can use, but these are not like general enough to cover every case.
Thank you.
Sure.
Okay. A quick one. We'll finish on time. Yeah, go
Hi,
ahead.
great presentation, by the way. Quick question. In the search space that you were talking about, like the grid, it seemed like for those, are they looking at just like the static hyperparameters? Like, for example, is there a range of, like, if I was interested in like
Yes.
learning rate, there's a range that I
Yeah, yeah.
specify, or
So the search space is user defined, and you can either do it randomly, right? So try different things and let me know. But there are also like iterative methods, right? So try a couple of things and then see how these perform, and based on that, schedule the next batch of jobs. So I mean, there are different flavors.
and then like just a quick follow-up to that, like there are methods out there where when you train a model, you can dynamically change the learning rate as well. So
Yes.
does this right now, it supports a static learning rate
No,
throughout, or
I mean,
does it?
the rate, right? The rate that you change the learning rate is a hyperparameter, right? So you can include it in your search space. Anything that controls the learning rate can be a hyperparameter. Okay, thank you.
Okay, so let's give a big hand to Noras. So with this, we conclude. Might be Wendy is there. Just call her, Wendy and others. Yes. So I think as you saw, like I mean, we have been here 3 days. Very quickly passed by. Okay. While we are talking all this presentation and all, they have been working on behind the scene. Okay, like Wendy, Tammy, Darren, and a lot of student volunteers to make sure everything is going on time. So thanks a lot again for all your help. And last but not least, the credit, a lot of credit goes to Karen. She's sitting here. She's at the top level. She and David Hudak, I think have been facilitating this mock to take place over the last 12 years, 12 out of 13 years. I think we have done here. So let's give a big hand to. Yeah. And also, I think all the volunteers who have been sitting here, can you please stand? I think including all the Nat and all come out. So they've been working also behind the scene just to. They have been like at least Nat, Rehan, Matt, and few others have now become AV engineers also. Okay, in addition to software engineers, doing all the AV things. So now they can provide some service. If anybody wants commercial service, they can go there. Okay, so give a big hand to all. So with this, we'll conclude. And remote people, thanks a lot again. And I think Nasser, you are saying, okay, many thanks to Mag team for organizing. Professor Nasser is actually, you would have seen, he's at in Saudi Arabia. So he has been joining this for all the last 3 days. I saw you attending from the very first day to the until now. I think it is very late.